Antarctica, a land of ice, wind, and silence, the coldest, driest, and most remote continent on Earth. It stretches over 14 million square kilometers, larger than Europe, yet almost entirely uninhabited. Humans have only been visiting it for a little more than a century, and even today, much of its vast interior remains unexplored for most of history. Antarctica was a blank space on maps, a mysterious southern land, theorized to exist simply because the Earth's symmetry seemed to demand it. Ancient geographers spoke of Terra Australis, the southern land, but no one truly knew what lay beneath the ice, or if it had ever been ice-free. Modern science tells us that Antarctica is covered by an ice sheet averaging 2 kilometers in thickness. This ice contains more than 90% of the world's fresh water, and holds within it a record of Earth's climate stretching back millions of years. Scientists drill deep into the ice, pulling ice cores and examining trapped air bubbles. These bubbles preserve samples of ancient atmospheres, allowing us to reconstruct temperatures, carbon dioxide levels, and even evidence of volcanic eruptions long past. Yet even as science explains much, mysteries remain. For beneath the ice lie mountains, valleys, and enormous lakes. Lake Vostok, for example, buried under more than 4 kilometers of ice, has been isolated for 15 million years. Scientists studying it have discovered strange microorganisms, life forms that survived without sunlight, without the surface conditions that normally sustain life. Could Antarctica have been a refuge for life long before humans walked the Earth? Maps from centuries ago suggest more. The Piri Reis map, created in 1513, shows parts of the southern continent, ice-free, coastlines drawn with a precision that still puzzles historians. Similarly, the Orontius Phineus map of 1531 depicts a landmass resembling Antarctica, yet it predates the continent's documented discovery by more than 3 centuries. These maps raise questions. How did ancient cartographers know what lay so far south, long before modern exploration? Speculation deepens when we consider ancient legends, stories of Atlantis, a civilization advanced beyond its time, suggest the possibility that humans once inhabited lands now hidden beneath ice. Could Antarctica have been home to an ancient society, lost to time as the ice sheets advanced and climates shifted? While no archaeological evidence has been confirmed, satellite imagery and radar scans show unusual formations, mountains and geometric shapes buried under the ice, shapes that some claim resemble pyramids or city grids, whether natural or artificial. The mere possibility stirs the imagination. Exploration of Antarctica began in earnest in the early 19th century. Captain James Cook crossed the Antarctic Circle in 1773, proving that a southern landmass existed, but he never saw the continent itself. Later, expeditions by Fabian Gottlieb von Bellingshausen, Charles Wilkes, and James Clark Ross mapped parts of the coast, enduring unimaginable conditions. Freezing temperatures, blizzards, and treacherous ice. The human body, unadapted to such extremes, struggled to survive. Many explorers suffered frostbite, scurvy, even death. The early 20th century brought a race to the South Pole. Roald Amundsen reached it first in 1911, followed shortly by Robert Falcon Scott, whose expedition ended tragically. Their journeys captured the world's imagination. Yet even as these heroes claimed the pole, the continent's interior remained largely unknown. It was, and still is, a frontier that challenges human ambition and imagination alike. The mid-20th century saw another kind of interest, one less about discovery and more about strategic presence. Operation Highjump, launched by the United States Navy in 1946-1947, involved thousands of men, ships, and aircraft, officially to train personnel and test equipment in extreme cold. But some historians suggest the operation had additional objectives: reconnaissance, surveying, and possibly investigating anomalous structures rumored under the ice. Whether true or exaggerated, it remains a point of fascination. Satellite technology today reveals even more. Radar systems penetrate the ice, mapping hidden lakes, subglacial mountains, and enormous valleys, Antarctica is not a barren wasteland. It's a landscape rich with geological features, ancient rock formations, and possibly clues to Earth's distant past. Scientists study it to understand plate tectonics, the movement of the continents and climate cycles. Each discovery opens more questions than answers. Consider the phenomenon of subglacial lakes, isolated for millions of years. They preserve microorganisms and chemical signatures that may reflect ancient ecosystems. Could these lakes harbor life forms that predate known species on the planet? Some researchers believe these extreme environments could even offer insight into extraterrestrial life. Places like Europa or Enceladus may share similar conditions. Antarctica becomes a laboratory, a window into extreme biology, and the resilience of life itself. Yet not all mysteries are scientific. Some involve human secrecy. During the Cold War, nations showed unusual interest in Antarctic bases, restricted zones, unusual military presence, and classified operations sparked speculation. Why were certain areas off limits, even to scientists? Could there be more beneath the ice than mere rock and snow? Perhaps remnants of lost technology or knowledge preserved from ancient civilizations. While no proof has been found, the questions remain: maps, ice cores, ancient legends, and unexplored landscapes converge into a compelling narrative. Antarctica may hold clues about climate cycles, ancient ecosystems, and perhaps even the history of human civilization itself. Every expedition, every drill, every satellite scan adds a fragment to a puzzle, one that stretches back millions of years, and may yet reshape our understanding of Earth. As we peer deeper into the frozen heart of the continent, imagination and evidence intertwine. The idea that Antarctica could hide a true history of the Earth is seductive. The thought of an untouched, hidden past locked beneath ice, waiting to be revealed, calls to our curiosity and challenges our assumptions. Yet caution is necessary. Science requires proof, not speculation alone. For every claim of pyramids or lost civilizations, every mysterious map or anomaly, researchers seek evidence. Confirming or debunking, Antarctica resists certainty. Its ice preserves both truth and illusion. Explorers, scientists, and theorists continue their work, braving the cold, the isolation, and the dangers inherent in extreme environments. Their discoveries advance knowledge, their unanswered questions sustain wonder. Antarctica remains the ultimate frontier, a place where Earth's past and perhaps secrets yet undiscovered await patient exploration. And so, the story of Antarctica begins not with what we know, but with what we do not. With each ice core drilled, each radar scan, each historical clue revisited, we take another step into the unknown. The frozen continent challenges our understanding, our imagination, and our determination to uncover the true history of our planet. Antarctica's true story lies beneath the ice. Miles of frozen crust conceal a landscape older than most civilizations. Subglacial mountains rise like silent giants, valleys stretch in frozen shadows, and liquid lakes lie trapped, untouched for millions of years. Modern science has only begun to reveal this hidden world. Radar and satellite imaging have revolutionized our understanding of the continent's interior. Ice-penetrating radar detects subglacial features, mapping mountains and river-like structures flowing beneath kilometers of ice. The Gamburtsev Mountains, for instance, lie completely buried beneath the East Antarctic ice sheet, larger than the Alps yet invisible, until advanced radar revealed them in the 2000s. How such massive formations survived hidden for millions of years, beneath shifting glaciers and extreme cold, remains a testament to the resilience of Earth's geological history. Beneath the ice lie lakes that have never touched the surface. Lake Vostok is the largest, more than 250 kilometers long, buried under 4 kilometers of ice. Its waters are sealed off from sunlight, and the atmosphere, isolated for 15 million years, life has persisted in forms still mysterious to scientists. Microbial life detected in samples shows adaptation to extreme cold, pressure, and isolation. These microorganisms survive in total darkness, without photosynthesis, relying on chemical energy from minerals and salts in the water. This suggests life can endure in places we once thought impossible. Other subglacial lakes include Lake Whillans, Lake Mercer, and Lake Subglacial Aurora. Each offers a window into the deep past. By studying their chemical composition, researchers hope to understand ancient climates, microbial evolution, and perhaps even analogs for life on other planets. Europa, one of Jupiter's moons, has oceans beneath ice layers. Antarctica becomes a terrestrial laboratory, helping us imagine how life could persist elsewhere in the solar system. Glacial ice itself holds remarkable records. As layers accumulate year after year, they trap air bubbles, dust, volcanic ash, and pollen from continents far away. Drilling into the ice produces cylinders of frozen time. Ice cores allow scientists to reconstruct Earth's climate over hundreds of thousands of years. They can detect sudden warming events, massive volcanic eruptions, even meteorite impacts. Antarctica preserves a continuous story of the planet's environmental history, waiting for careful interpretation. Yet beyond life and climate, the land beneath Antarctica is strange. Subglacial mountains and valleys defy simple explanation. Some formations appear geometric, like pyramids or terraced plateaus. Satellite radar images reveal outlines that spark curiosity and speculation. Are these purely natural? Or could they be evidence of something lost to time, structures buried under ice sheets formed over tens of thousands of years? Scientists caution against hasty conclusions, yet the possibility lingers. Antarctica has also shifted dramatically through Earth's history. During the Cretaceous period, more than 65 million years ago, the continent was part of Gondwana, a vast supercontinent that included South America, Africa, India, and Australia. Fossilized plants, dinosaurs, and even freshwater fish from that era have been found beneath the ice. These discoveries prove that Antarctica was once warm, fertile, capable of sustaining life in abundance. The ice we see today is a relatively recent phenomenon, frozen over in the last 34 million years. This hidden history raises questions about human myths and ancient knowledge. If Antarctica was once ice-free and inhabited by life, could early humans or lost civilizations have reached it? While no archaeological evidence has been confirmed, legends of Atlantis and other ancient societies often describe lands that were destroyed by floods, ice, or sudden climate change. Could these stories have originated from a continent now hidden beneath ice? Exploration beneath the ice remains challenging. Drilling into kilometers of frozen crust requires precision engineering, specialized equipment, and careful planning. Contamination of pristine subglacial lakes is a major concern. Scientists must prevent modern microorganisms from altering these ancient ecosystems. Robotic probes and sterile drilling techniques allow sampling without disrupting fragile environments. Each mission uncovers new data and more mysteries. Geological studies suggest Antarctica has moved across the globe over millions of years. Plate tectonics shifted the continent from temperate latitudes to the extreme south. Ice sheets expanded as the continent cooled, dramatically reshaping landscapes, burying ecosystems, and preserving a fossil record frozen in time. By understanding these processes, we gain insight into the planet's long-term climate cycles and geological evolution. Seismic studies reveal layers of rock beneath the ice. Some suggest sudden events, like massive landslides or meteor impacts, shape the subglacial topography. Could these catastrophic events have influenced the course of life on Earth? Did climate shifts trigger mass extinctions or migration patterns we do not yet understand? Antarctica's buried terrain preserves the clues, but demands careful study to interpret accurately. Water flows silently beneath the ice. Subglacial rivers move thousands of cubic meters of water per second, carving channels, lubricating glaciers, influencing ice sheet stability. These hidden rivers play a crucial role in global sea levels. Understanding them is vital not only for science, but for predicting how climate change may impact humanity. Antarctica's secret waterways connect the past, the present, and the future. The human fascination with what lies beneath Antarctica has persisted for centuries. Explorers, scientists, and theorists alike are drawn by the allure of the unknown. Radar images, ice cores, and geological surveys provide tantalizing glimpses, but also leave vast areas unexplored. Each discovery brings more questions than answers. Every mountain, lake, or valley may hold secrets that could redefine our understanding of Earth. And so, Antarctica remains a paradox, a continent that is at once the most studied and the least known. Its ice preserves truth, but also conceals it. Beneath the frozen surface, life endures. Landscapes shift and history waits for those patient enough to uncover it. The story beneath the ice is far from complete. It is a tale of extremes, survival, hidden geographies, and mysteries that may forever elude full understanding. Each subglacial mountain and lake, each ice core drilled, brings us closer to a picture of Earth's deep past, and perhaps hints at truths humanity has only begun to imagine. Long before Antarctica was officially discovered, humans speculated about a vast southern land known as Terra Australis, a land believed necessary to balance the continents in the northern hemisphere. Ancient geographers from Greece and Rome included it in their maps, often as a blank or vaguely drawn expanse. Theories of a southern continent persisted for centuries, fueled by philosophical reasoning, sailors' tales, and fragmentary evidence. One of the most compelling historical artifacts is the Piri Reis map, created in 1513, drawn by the Ottoman admiral and cartographer Piri Reis. It depicts parts of South America, Africa, and remarkably, what some interpret as Antarctica. The coastline appears ice-free, detailed with precision that is difficult to explain given the time period. Some historians argue that Piri Reis used older maps, possibly of unknown origin. Others suggest coincidence. Yet the map has fascinated scholars and mystery enthusiasts alike for decades. What sources did Piri Reis consult? Were there records from earlier civilizations, now lost to time? Another enigmatic document is the Orontius Phineus map of 1531, drawn by the French cartographer Oronce Finet. It shows a southern landmass that resembles Antarctica, complete with mountain ranges and coastal outlines. Yet this map predates the confirmed discovery of the continent by nearly 3 centuries. How could cartographers have obtained such accurate information without modern exploration tools? Some suggest that explorers may have reached Antarctica before 1500, leaving records that were subsequently lost or hidden. Others propose that ancient civilizations possessed knowledge now forgotten. Even more curious are legends from different cultures. Myths speak of lost lands in the far south, tales of kingdoms swallowed by ice or floods. Some researchers speculate that these stories may be distant memories of Antarctica before it froze completely. Geological studies indicate that during the mid-Cretaceous period, Antarctica was warm, forested, and inhabited by flora and fauna. Could oral traditions, passed down over millennia, have preserved fragments of knowledge about this distant land? Early European explorers often brought back incomplete, contradictory accounts. Captain James Cook crossed the Antarctic Circle in 1773, proving the existence of southern land. Yet he never sighted the continent itself. Subsequent explorers documented icebergs, cold seas, and hints of land, but maps remained inaccurate. Until aerial reconnaissance and satellite imagery, Antarctica's coastline was poorly understood. These inaccuracies may have fueled speculation and contributed to myths of hidden civilizations or unknown geographies. Some proponents of alternative history point to strange correlations between ancient maps and modern Antarctic geography. Geologists note that certain formations, mountains, and valleys depicted on historical maps align with features now revealed by satellite radar. Could this indicate lost knowledge, observations passed down from unknown sources, or mere coincidence? No definitive proof exists, but the questions persist. The Antarctic Treaty, established in 1959, restricted military activity and mineral exploitation, limiting access to many parts of the continent, fueled speculation about secret bases or undisclosed discoveries. The combination of limited access, extreme climate, and historical mystery creates fertile ground for what-if scenarios. Could early explorers or ancient civilizations have left traces, now buried beneath ice sheets? The study of ice cores and geology supports some possibilities. Scientists have found evidence of ancient climates, warmer periods, and ice-free regions. Fossilized plants and freshwater fish prove that Antarctica once supported life. These findings align with speculative interpretations of ancient maps, suggesting the continent was not always the frozen wasteland we know today. Could the Piri Reis map and Orontius Phineus map reflect this prehistoric geography? Additionally, the Antarctic Peninsula has peculiar features that invite questions. Geological surveys reveal volcanic formations, rock outcrops, and sediment layers that indicate periods of exposure above ice. Could these areas have been visible to ancient sailors navigating the southern oceans? The precise mapping of some features, long before modern instruments existed, remains an enigma. Cartographic anomalies are not limited to the South. Ancient civilizations often depicted the world differently. The Egyptians, Greeks, and Polynesians possessed sophisticated navigational knowledge. Using stars, currents, and landmarks, they may have ventured farther than conventional history records. Could fragments of their observations have been preserved and incorporated into maps like Piri Reis, passed down across cultures, refined over centuries before being forgotten? Historical speculation intersects with geology and climatology. Plate tectonics indicates that Antarctica's position shifted over millions of years. Once connected to Gondwana, it moved south. Altering climate, ice sheets advanced, covering what may have been habitable lands. Could maps drawn in antiquity represent a continent before these ice sheets formed? The possibility exists, though evidence is circumstantial. Some historians caution against overinterpretation. The apparent accuracy of ancient maps could be coincidental or the result of creative cartography. Yet the consistency of certain features with modern topography is difficult to dismiss entirely. Whether intentional or accidental, it sparks wonder and invites further investigation. Exploration of historical documents reveals more than maps. Logs, diaries, and notes from early explorers sometimes describe unexpected topography, strange rock formations, and conditions that seem inconsistent with their supposed locations. Could these be references to regions of Antarctica briefly glimpsed before the continent froze completely, or exaggerations meant to awe and mystify patrons? Even scientific publications occasionally fuel speculation. Some geologists argue that tectonic evidence supports the possibility of ice-free regions within the last 10,000 years. If true, small habitable pockets may have existed, accessible to migratory humans or other intelligent species. Could these remnants have inspired myths and maps preserved for centuries? The interplay between science and speculation creates a narrative as compelling as any adventure story. Each map, each legend, each geological anomaly serves as a piece of a puzzle, hinting at a hidden chapter of Earth's history, one that may lie buried beneath the ice, waiting to be discovered. Radar, satellite imagery, and ice drilling now allow us to test these old hypotheses. Scientists probe the continent with lasers, sound waves, and satellites, mapping hidden mountains, valleys, and subglacial lakes, confirming some ancient formations, challenging interpretations of others. The dialogue between history, legend, and science continues. Could Antarctica have been observed by humans long before officially recorded history? Did ancient civilizations possess knowledge that modern science is only beginning to confirm? The evidence is tantalizing, incomplete, and enigmatic. Each discovery inspires more questions than answers. And so, the story of ancient maps and strange clues remains an open chapter, a bridge between documented history and the mysteries of Earth's deep past. Antarctica, hidden beneath layers of ice, whispers secrets of a world that once was, and may yet reveal truths humanity has forgotten. The Piri Reis map, The Orontius Phineus map, legends of lost lands, ice cores, radar scans, each offers a glimpse into possibilities. Each invites the mind to wonder, to ask, what if? What if the frozen continent holds memories of Earth's history that we have yet to fully comprehend? Long before the relentless cold of the modern Antarctic, the continent was a very different world, a land of green forests, rivers winding across fertile plains, and a climate capable of sustaining life. Evidence from fossilized plants, ancient pollen, and dinosaur remains tells a story few imagine. Antarctica was not always the frozen desert we know today. During the Cretaceous period, roughly 145 to 66 million years ago, Antarctica formed part of the supercontinent Gondwana, connected to South America, Africa, India, and Australia. Fossilized ferns and conifers discovered in the Transantarctic mountains suggest a temperate climate, occasional warm summers, and ecosystems rich in life. Dinosaurs, both herbivorous and carnivorous, roamed this lush land. Their footprints and skeletal remains preserved in rock provide a window into a world that existed long before humans. Marine fossils reveal that ancient seas surrounding the continent teemed with life. Ammonites, mollusks, and early fish species thrived in the warm oceans. Even today, paleontologists can trace how continents shifted, oceans changed, and ecosystems evolved. The land that is now encased in ice once experienced the cycles of growth, decay, and migration that define living worlds. Evidence suggests that as the continents drifted, Antarctica moved gradually southward. Climates cooled. Ice sheets began to form, covering much of the interior. But even as ice advanced, pockets of habitable land persisted, coastal regions, volcanic geothermal zones, areas where life could endure. Fossils from these transitional periods reveal plants and small animals adapted to cold, hinting at resilience and continuity of ecosystems. Geologists study sedimentary rock layers to understand these transitions. They reveal periods of ice retreat, flooding, and volcanic activity. Ice cores drilled in coastal regions preserve pollen and microorganisms, which indicate periods when the land was partially ice-free. Perhaps during these warmer windows, life could have thrived. Maybe even human explorers or transient civilizations could have survived. The concept of Antarctica as a dynamic, changing land challenges conventional assumptions. Modern maps suggest uniform ice, but beneath, the land tells a story of cycles, glaciation, and ecological shifts. Ice is not permanent. It grows, it retreats. It reshapes the landscape. Subglacial mountains once stood as towering peaks above rivers and forests. Valleys formed natural corridors. Ecosystems thrived, and then were buried beneath ice. Climate data from ice cores also supports this. Carbon dioxide levels, trapped in bubbles, show fluctuations, warming periods lasting thousands of years, followed by sudden cooling. These cycles may have permitted temporary openings in the ice, brief windows when life could flourish. Perhaps these were the moments captured indirectly by ancient myths or obscure maps, when the continent was visible, accessible, and remembered in human memory. The fossil record offers clues not only about flora, but fauna as well. Early reptiles, amphibians, and mammals left traces in sediment layers, creatures adapted to warmer Antarctic climates, some of which migrated from connected continents. Others evolved in isolation, forming unique species. Antarctica was, for a time, an ecological island, a world separate from the frozen wilderness we know today. Volcanic activity played a role in preserving life in isolated zones. Geothermal hotspots may have created temperate microclimates, areas where flora persisted, animals survived, perhaps even early hominids. If ancient migration theories hold any plausibility, such zones could explain pockets of biodiversity found in fossil and microbial records. A hidden, habitable Antarctica might have existed for thousands of years. The transition from a warm, life-filled land to a frozen desert was not instantaneous. Ice sheets expanded over millions of years, reshaping coastlines, burying mountains and valleys beneath kilometers of ice. The land that once sustained rich ecosystems was gradually rendered inhospitable. Life retreated, adapted, or vanished, leaving only fossils and clues hidden beneath the ice. Geologists also note that Antarctica's ice history includes dramatic fluctuations, periods of melting, sudden refreezing, glacial surges. These events may have preserved structures, natural or artificial, buried and protected for millennia. Could remnants of advanced civilizations, if they ever existed, have survived such transitions? The possibility fuels the imagination and the search for answers. Scientists studying meteorites and ancient rock formations have found evidence of environmental extremes, asteroid impacts, massive flooding, volcanic eruptions, earth-shaping events that may have influenced climate, wiped out life in some regions, or altered migration patterns. The frozen continent preserves traces of these cataclysms, offering insight into Earth's resilience and the fragility of life. In modern times, Antarctica continues to surprise researchers. Geophysical surveys reveal ridges, valleys, and hidden lakes beneath ice sheets. The subglacial landscape is a record of the continent's pre-ice history. Each hidden mountain or lake may correspond to an era when the land was alive, fertile, and possibly visited by unknown travelers. Ancient life, preserved in rock and ice, whispers of a world forgotten. This history challenges assumptions about human knowledge. Ancient maps depicting a southern land, geological evidence of temperate zones, fossilized ecosystems. Could fragments of this lost world have been known to civilizations before recorded history? Perhaps oral traditions, myths, or symbolic representations encode distant memories of a green, life-filled Antarctica. Though speculative, the evidence suggests the past was far more complex than we imagine. The story of pre-ice Antarctica is not only one of life and climate, but of opportunity, a frozen continent today, a fertile, thriving land millions of years ago. The contrast inspires awe and curiosity. Each glacier, each sediment layer, each fossil uncovered is a testament to a dynamic Earth, one that changes dramatically over time, yet preserves memories of what once was. And so, the land before the ice remains a frontier of discovery, a chapter of Earth's history partially hidden, waiting for patient observers to decode its secrets. The frozen wilderness is not merely desolate, it is a palimpsest layers of history, biology and geology inscribed over millions of years, offering clues to the world that existed before Antarctica became the ultimate frozen frontier. The continent before the ice, lush, fertile, alive, is a vision supported by science, yet rich in mystery. Every rock layer, fossil and ice core provides a fragment of truth and a doorway to imagination. What stories did this lost Antarctica hold, and could we ever fully uncover them? Only time, patience, and exploration will tell. The idea of lost civilizations captures the imagination. Across cultures and centuries, humans have speculated about advanced societies that existed long before recorded history. From Atlantis to Lemuria, tales of civilizations swallowed by the sea, buried beneath sand, or encased in ice, persist in mythology. Could Antarctica be one such forgotten land? Ancient texts and oral traditions often speak of lands in the far south, places of extraordinary wealth, knowledge, and power. Plato's account of Atlantis describes an advanced civilization, existing 10,000 years before his own time, a society with cities, engineering marvels, and cultural achievements far beyond neighboring peoples. Though most historians view Atlantis as allegorical, some argue that Plato may have preserved memory of a real land, possibly one now buried beneath ice. In other cultures, similar legends emerge. In South American myth, stories describe sunken lands, ancient knowledge lost beneath shifting oceans. Some Polynesian traditions speak of southern islands that disappeared. Scholars suggest these may reflect collective memory of rising seas or climate change. Could these stories indirectly reference Antarctica before the ice sheets fully advanced? Physical evidence provides tantalizing hints. Geologists and glaciologists have found formations beneath the Antarctic ice that appear unusual geometric patterns, elevated plateaus and hidden valleys. While most are likely natural, the mere presence of formations resembling human planning fuels speculation. Could these be remnants of settlements, temples, or other constructions, lost to time, encased in ice for thousands of years? Subglacial lakes add another layer of mystery. Isolated ecosystems have survived without sunlight for millions of years. Microbial life has adapted to extreme conditions. Could remnants of more complex life, or traces of a lost society, somehow have persisted in hidden geothermal regions? While no evidence supports intelligent life beneath the ice, the idea captures the imagination and invites careful scientific scrutiny. The stories of human exploration in pre-modern eras also raise questions. Early cartographers and explorers sometimes reported land south of the known continents. Accounts describe strange features, mountains, or rivers glimpsed through ice or mist. Could these have been fleeting observations of remnants of an ancient civilization, long buried as the ice advanced? Some historians caution that these reports were exaggerated or misinterpreted, yet they persist in the historical record. The Antarctic ice sheet itself preserves history. Sediment cores from beneath the glaciers reveal periods of warming, suggesting ice-free regions. For thousands of years, portions of the continent may have been habitable, a green Antarctica, with rivers, lakes, and forests. This possibility aligns with legends of lost lands, regions that suddenly became inhospitable, and whose memory survived in myth. The allure of lost civilizations is also reflected in modern expeditions. Operation Highjump in 1946-47, led by the United States Navy, has inspired numerous conspiracy theories. Some claim that teams investigated anomalies beneath the ice, possibly remnants of an advanced society. The official record emphasizes training and equipment testing, yet the operation's scale, the number of personnel and resources deployed, fuels speculation. Could Antarctica have held secrets worth investigating at a strategic level? The Peary Rise map and Orontius Phineus map add another layer to the mystery. Accurate depictions of southern coastlines before official discovery. Could these maps have originated from ancient knowledge, passed down through lost civilizations, now buried beneath ice sheets? Scholars debate the sources, but the correspondence between map features and subglacial geography is intriguing. Even if coincidental, it invites further exploration. Some researchers have examined anomalies in ice-free coastal regions, strange rock formations, peculiar alignments of mountains, and unusual sediment patterns. While science generally explains these as natural phenomena, imaginative interpretations suggest potential foundations of structures, roads, terraces, or other human-made features. Whether true or not, these observations keep the legend alive and sustain curiosity. Antarctica's geological history supports the possibility of human or advanced activity. During warmer periods, the continent was accessible, connected to other landmasses through lower sea levels. It was feasible for people to migrate, settle temporarily, or leave traces. Fossil evidence of flora and fauna proves life thrived. Could intelligent societies have briefly existed, leaving impressions now buried beneath kilometers of ice? The concept of memory preserved in myth is also compelling. Tales of Atlantis, sunken lands, and lost knowledge may reflect collective memory. Communities often encode history symbolically. Myths act as vessels, passing down fragments of truth through generations. In this light, Antarctic legends could be a distant echo of a real world lost beneath ice sheets. Modern technology allows us to investigate these legends. Satellite imagery, ice-penetrating radar, and subglacial mapping reveal mountains, valleys, and lakes previously unknown. Each discovery inspires new interpretations. Could formations resembling pyramids or grids be natural? Or could they represent remnants of construction, evidence of a civilization erased by ice and time? The debate continues. The Antarctic Treaty of 1959 also fuels speculation. restricting military activity and mineral exploitation. It limits access to some regions, preserving the mystery of hidden landscapes, restricted areas, unexplored regions, and extreme conditions create the perfect environment for imagination. Could humanity's lost history remain sealed beneath ice sheets, protected by harsh climates and legal boundaries? Legends of lost civilizations inspire scientific inquiry. They drive paleoclimatology, geology, and archaeology to explore the continent more deeply. Hypotheses are tested, anomalies investigated, ice cores drilled, and satellite scans conducted. Even if no human-built structures are found, the pursuit expands knowledge of Earth's past, revealing ecosystems, climate history, and the resilience of life. Stories of Atlantis and similar myths also intersect with climate science. Rising and falling sea levels, ice sheet growth, and tectonic shifts could have erased evidence of human activity. What once was habitable, even populated, may now lie buried and inaccessible. This alignment of legend and environmental change reinforces the fascination with Antarctica, a frozen time capsule, preserving fragments of Earth's forgotten chapters. Ultimately, the continent is both known and unknown. Science explains part of the story, while legend and speculation fill the rest. Antarctica's ice hides clues about lost civilizations, whether human, symbolic, or imagined. The myths act as bridges between fact and wonder, inspiring exploration, scientific inquiry, and imagination. And so legends of lost civilizations endure not necessarily as proof, but as invitations to explore, to investigate, to consider that Earth's history may be more complex than our textbooks describe. Each subglacial lake, each fossil, each unexplored valley adds depth to the narrative. Antarctica remains a canvas, a continent frozen in time, holding the echoes of life and perhaps civilization waiting to be discovered. Earth is not as stable as it may appear. Its axis wobbles, plates shift, and climates change. Catastrophic events have shaped continents, oceans, and ecosystems. Antarctica, remote and frozen, carries evidence of these forces. Buried in ice, rock, and sediment, scientists have long studied the concept of true polar wander, the movement of Earth's solid exterior relative to its rotational axis. While slow, these shifts can dramatically affect climate, altering ocean currents, wind patterns, and the distribution of ice sheets. Geological evidence suggests that Antarctica may have experienced significant positional changes over millions of years, contributing to its transition from a green, fertile land to a frozen desert. Sudden events, catastrophes on a geological scale, also leave marks in the record. Massive volcanic eruptions, like those of the Deccan Traps, released enormous amounts of carbon dioxide, triggering warming periods. Glaciers advanced and retreated in cycles, altering landscapes, rivers, and ecosystems. Antarctica was not immune. Layers of ash and sediment found in ice cores provide a glimpse of these ancient cataclysms. Meteorite impacts have similarly shaped the continent's history. Large craters detected beneath the ice, evidence of collisions that would have caused massive tsunamis. Fires and atmospheric disturbances. Ice cores preserve traces of sudden temperature shifts and chemical anomalies, suggesting environmental upheavals. Could these catastrophes have influenced early ecosystems, and hypothetically, the fate of transient human or advanced societies? During periods of extreme warming, ice sheets melted, exposing previously buried land. Rivers flowed, lakes expanded, ecosystems thrived, only to be abruptly refrozen during sudden cooling events. These oscillations, rapid on a geological timescale, demonstrate Antarctica's dynamic history. Life had to adapt, retreat, or perish. Each freeze-thaw cycle left its mark on the landscape, preserving evidence of Earth's resilience and vulnerability. Pole shifts also affect sea levels globally. As ice melted and reformed, oceans rose and fell. Coastal civilizations in distant continents experienced flooding. Myths of sunken lands, lost cities, and cataclysmic events may have roots in these real phenomena. Could some of the world's oldest legends, like Atlantis or Lemuria, reflect memories of sudden sea level changes triggered by Antarctic ice sheet fluctuations? Geological evidence supports rapid climate events. Layers of sediment with sudden chemical changes indicate abrupt shifts. Ice cores reveal spikes in greenhouse gases. Volcanic ash and particulate matter, each layer tells a story, not just of climate, but of environmental stress, potentially catastrophic to life. Antarctica's frozen surface preserves these events with extraordinary fidelity. Subglacial formations may themselves bear evidence of catastrophe, valleys carved by sudden glacial surges, rocks displaced by immense pressures. Lakes suddenly flooded, each hidden feature could be the result of a long-ago disaster, preserved beneath ice for millennia, waiting for discovery. Even minor pole shifts can have profound consequences, shifting the distribution of sunlight, altering growing seasons, changing oceanic circulation. Life must respond, migrate, adapt, or die in Antarctica. Plant and animal fossils indicate periods of survival despite extreme environmental changes. Microbes endured in isolated lakes, suggesting that life finds a way, even in the harshest conditions. Some researchers propose more dramatic hypotheses, rapid pole shifts occurring over centuries or decades, rather than millennia. Could such events explain sudden climate anomalies recorded in ice cores, or abrupt disappearance of species in the fossil record? Evidence remains circumstantial, but it fuels imagination and the search for understanding. Earthquakes beneath the ice also played a role. Subglacial seismic activity influences ice flow, can trigger sudden collapses or floods, reshape valleys, expose rock formations. Perhaps these dynamic forces contributed to the preservation of features that some speculate could be artificial. The combination of geological processes creates landscapes both natural and enigmatic. Historical speculation intersects with modern science. Some theorists suggest that knowledge of catastrophic pole shifts may have been preserved in ancient myths. Civilizations could have witnessed rapid environmental changes, preserving these events as allegory, myth, or symbolic storytelling. Antarctica's buried history may hold a key, a frozen record of disasters that shaped life on Earth. Volcanic eruptions beneath ice sheets create additional complexity. Heat melts overlying ice, forms subglacial lakes, triggers sudden floods. Each eruption leaves chemical signatures, layers of tephra preserved for millions of years. Life beneath ice may adapt, but surface ecosystems can be devastated. These processes illustrate the interconnectedness of Earth's geology, climate, and biology. The concept of global catastrophes ties Antarctica to human history. Rising seas from melting ice sheets, earthquakes, and volcanic eruptions may have influenced migration patterns. The disappearance of some early civilizations could align with such events. Could legends of lost southern lands correspond to real catastrophes recorded in Antarctica's frozen archives? Modern research continues to explore these possibilities. Scientists use satellite monitoring, radar mapping, ice core analysis, and subglacial drilling. Each discovery adds detail to the story of catastrophe, yet every answer raises new questions. What events shaped Antarctica's landscape in ways we cannot yet fully comprehend? Could these forces have erased traces of life or civilization, leaving only tantalizing fragments? As the story unfolds, Antarctica emerges as a continent shaped by extremes, a land where slow processes like pole shifts and ice sheet expansion intersect with sudden catastrophes, meteorite impacts, volcanic eruptions, glacial surges. Each layer of ice and sediment preserves a record, a chapter of Earth's history, silent, frozen, and waiting for interpretation. In studying these cataclysms, we gain insight not only into Antarctica, but into Earth as a whole. Climate, geology, and life are interconnected. Sudden events remind us of the planet's volatility, the fragility of ecosystems, and the resilience of life that adapts, survives, or vanishes. The frozen continent holds clues not just of survival, but of transformation. Pole shifts and catastrophes left enduring marks beneath kilometers of ice. Each anomaly, hidden valley, subglacial lake, provides a potential window into events that shape the Earth's surface and possibly the course of human history. And so, the story of pole shifts and catastrophes is a tale of extremes, a narrative that spans millions of years, connecting geological processes, climate change, and the endurance of life. Antarctica preserves these stories with unparalleled clarity. Its ice is a time capsule, recording disasters, transformations, and resilience, waiting for patient observers to decode its secrets. Beneath the vast Antarctic ice sheet lies a world unseen by human eyes, a hidden network of lakes, rivers, and reservoirs, trapped beneath kilometers of ice. These subglacial lakes are isolated, untouched by sunlight, and shielded from the surface for millions of years. They hold secrets about life, climate, and Earth's history. Lake Vostok, the largest and most famous, stretches over 250 kilometers, buried under nearly 4 kilometers of ice. Its waters have been isolated for up to 15 million years. Scientists drilling through the ice faced extraordinary challenges, avoiding contamination, preserving ancient microbes, extracting samples without altering the lake's pristine environment. The data revealed life, resilient, adaptive, surviving without sunlight or photosynthesis, relying instead on chemical energy from minerals and salts in the water. Smaller lakes, such as Lake Whillans and Lake Mercer, also host unique ecosystems. Microbes found here survive in extreme cold, high pressure, and complete darkness. These microorganisms provide a model for understanding life in extreme conditions. If life can persist under Antarctica's ice, could similar forms exist on icy moons or exoplanets, like Europa or Enceladus? Subglacial lakes influence Antarctica's ice dynamics. Water flowing beneath glaciers lubricates the ice, affects movement rates, and contributes to ice sheet stability. Understanding these lakes is crucial, not only for understanding local ecosystems, but also for predicting global sea level rise. Antarctica's hidden waterways are an integral part of Earth's environmental balance. Geophysical surveys reveal thousands of such lakes. Many are interconnected, forming a subterranean network. Channels carved by ancient rivers transport water, sediment, and nutrients. Some lakes may experience occasional flooding, suddenly altering the landscape beneath kilometers of ice. Each event leaves traces in sediment layers, ice cores, and geological formations, preserving a record of environmental change. These lakes also provide insight into ancient climate. Samples of water and sediment contain chemical signatures, isotopes, and microorganisms that reveal conditions over millions of years. Scientists can reconstruct temperature fluctuations, periods of warming and cooling, volcanic activity, and atmospheric changes. Antarctica's frozen lakes are natural archives, preserving the planet's history. The extreme isolation of these lakes raises fascinating possibilities. Life within them may have evolved independently for millions of years, adapting to unique chemical environments, extreme pressures, and total darkness. These ecosystems challenge our understanding of biology, revealing the resilience of life and the diversity of survival strategies. Lake Vostok alone has yielded microorganisms capable of metabolizing iron, sulfur, and nitrogen compounds. These microbes provide clues about ancient metabolic pathways, possibly used in early Earth ecosystems. Could such life forms resemble organisms on other planets, or even life that predates modern Earth species? The implications are profound for astrobiology, evolutionary biology, and understanding life's limits. Exploration of these lakes is technically demanding. Drilling through kilometers of ice requires precision engineering. Sterile techniques prevent contamination. Robotic probes enter the lakes, collecting samples, capturing microbial life, chemical composition, and sediment layers without disturbing these fragile ecosystems. Each mission expands knowledge, yet every discovery raises new questions. Subglacial lakes also preserve geological history. Layers of sediment reveal past climates, periods of ice retreat and advance volcanic ash deposits, even meteorite impacts. Water chemistry captures changes in nutrient levels, salinity, and microbial populations. Antarctica's frozen lakes are not static, they are dynamic. evolving over millions of years. The study of these lakes also informs our understanding of Earth's water cycle, how water moves beneath ice sheets, how ice melts and refreezes, and how subglacial rivers interact with lakes. This knowledge is essential for predicting the effects of climate change on glaciers, ice sheets, and global sea levels. Antarctica's hidden waters are both scientific laboratories and indicators of planetary health. The discovery of life in such extreme conditions challenges assumptions about habitability. In a place without sunlight, without oxygen, organisms persist, metabolizing minerals, adapting to cold and pressure. Life, it seems, finds a way. Could similar ecosystems exist elsewhere in our solar system or beyond? Antarctica becomes a terrestrial analog, helping scientists prepare for exploration of icy moons and exoplanets. Subglacial lakes also raise questions about Earth's ancient history. Could they preserve remnants of earlier life, perhaps even extinct species, or chemical traces of ancient ecosystems that predate the ice sheet? Sediment cores may contain DNA, proteins, or chemical signatures of life forms long vanished from the surface. Antarctica's frozen lakes are archives, holding evidence of evolutionary history and the persistence of life in extreme conditions. The lake's stability is remarkable. Water has remained liquid under immense pressure and extreme cold, shielded from cosmic radiation and surface disturbances. Microbial life persists in isolation, slowly evolving, adapting, surviving. Each lake is a laboratory of evolutionary innovation, offering insights impossible to replicate elsewhere. Some scientists speculate about the possibility of complex life, or even remnants of higher organisms, adapted to subglacial conditions. While no evidence currently supports this, the extreme longevity and isolation of these ecosystems make it a tantalizing area of study. Antarctica's frozen lakes challenge the boundary between imagination and science. The frozen lakes also preserve evidence of past catastrophes. Subglacial sediments contain chemical anomalies, traces of volcanic eruptions, meteor impacts, sudden climate shifts. Each layer tells a story of survival, adaptation, and environmental change. Ice cores and lake sediments are intertwined, offering a comprehensive record of the continent's dynamic past. These lakes remain largely unexplored. Over 400 subglacial lakes have been identified. Only a few have been directly sampled. Each new discovery expands our understanding from microbial ecology to planetary science. They hold answers to questions about life's resilience, climate history, and the evolution of Antarctica itself. And so, the frozen lakes beneath Antarctica are more than just bodies of water. They are hidden worlds, teeming with microbial life, archives of geological and biological history, and natural laboratories for understanding extremes of habitability. Each lake is a window into the past and a bridge to the future. Exploring them requires patience, precision, and imagination. Antarctica's subglacial lakes are silent witnesses, preserving life and history in total darkness. For scientists, they are laboratories for humanity. They are symbols of endurance, mystery, and the hidden complexity of our planet. The story of the frozen lakes is one of survival, adaptation, and secrets locked beneath ice. Antarctica holds these mysteries in its frozen embrace, and humanity has only begun to uncover them. Beneath the vast white expanse of Antarctica lies a hidden world, a continent of mountains, valleys, and plateaus concealed beneath kilometers of ice. These subglacial landscapes are largely invisible to the naked eye, yet modern technology reveals their complexity. The continent is not just a frozen flatland. It is sculpted, dramatic, and full of geological secrets. One of the most astonishing discoveries is the Gamburtsev mountain range, a chain of peaks comparable in size to the European Alps, entirely buried beneath ice, extending over 1,200 kilometers. The Gamburtsevs were unknown until the late 20th century, detected using ice-penetrating radar and seismic surveys. Their existence raises fundamental questions. How did such a mountain range form? And why has it remained hidden under ice for millions of years? Geologists hypothesize that the Gamburtsev Mountains are ancient, possibly formed over 1 billion years ago. During the supercontinent Rodinia, tectonic collisions created towering peaks. Over eons, ice advanced and retreated, burying these mountains. Yet the structure remained largely intact. This hidden topography preserves a record of Earth's geological evolution. Unlike almost anywhere else on the planet, valleys and subglacial basins complement the mountains. Deep troughs carved by ancient rivers, or shaped by glacial flow, hidden lakes sit in these depressions, forming isolated ecosystems. Some valleys may channel ice movement, lubricating glaciers as they flow toward the coast. Antarctica's subglacial topography is both dynamic and enduring, a testament to the power of geological processes. The discovery of these mountains and valleys also challenges our understanding of ice sheet dynamics. How does ice flow over hidden peaks and fill subglacial basins? Ice-penetrating radar shows that ice thickness varies dramatically, from a few hundred meters in some valleys to over 4 kilometers above peaks. The hidden landscape influences glacial stability, affecting global sea level predictions. The Gamburtsev Mountains also possess intriguing features: sharp ridges, plateau-like regions, and abrupt cliffs, suggestive of tectonic uplift and erosion. Unlike mountains exposed to the atmosphere, these peaks have been preserved beneath ice, protected from wind and weathering, allowing scientists to study ancient rock formations that elsewhere would have been eroded. Antarctica is a natural geological archive, preserving Earth's history beneath frozen layers. Other subglacial ranges and valleys are equally fascinating. Satellite data reveals smaller ranges, isolated peaks and deep trenches. The Vostok subglacial highlands, Shackleton Range, and various unnamed formations create a hidden landscape of immense scale. These structures influence ice flow, subglacial lakes, and even microbial ecosystems. Antarctica is alive. Beneath its frozen surface, geophysical surveys have revealed anomalous features, dome-like formations, ridges running in parallel, and depressions with unusual shapes. While many are natural, their geometry invites speculation. Could hidden plateaus have supported life, or even ancient human or animal activity during ice-free periods? Though evidence for civilization is absent, the imagination is inspired by these dramatic landscapes. The subglacial valleys also play a critical role in climate and hydrology. Water trapped in subglacial lakes, or flowing beneath ice sheets, lubricates glaciers, influences ice movement, and affects how quickly ice responds to warming. Studying these valleys helps predict the future of Antarctic ice sheets and global sea levels. The continent's hidden features are not just geological wonders, they are climate regulators. The scale of these hidden mountains and valleys is difficult to comprehend. Peaks rise thousands of meters, while valleys plunge deep. Ice sheets flow silently over these features, shaping and reshaping them over millennia. Each layer of ice preserves a history, recording advances and retreats of glaciers, volcanic activity, and tectonic shifts. Antarctica is a living archive of Earth's dynamic processes. The preservation of ancient geology beneath ice offers clues about the planet's past. Rock samples from subglacial drilling reveal mineral compositions, tectonic history, and evidence of past climates. Some formations date back over 1 billion years, providing insight into supercontinent cycles, mountain formation, and the long-term evolution of Earth's crust, hidden beneath ice. These mountains are a geological treasure trove. The existence of such dramatic subglacial landscapes also fuels speculation. Some researchers suggest that ice-free periods could have exposed hidden valleys and peaks, possibly supporting transient ecosystems, rivers, and flora. Could isolated regions have remained habitable long enough to sustain life during warmer windows? Geological evidence suggests that localized ice-free zones did exist, hinting at pockets of opportunity in an otherwise frozen land. Antarctica's hidden topography also affects exploration and scientific research. Mapping mountains and valleys beneath ice is challenging, requiring radar, seismic surveys, and satellite imaging. Each mission reveals more of the continent's complexity, revealing peaks, ridges, and basins that challenge preconceptions. Antarctica is far from uniform. Its hidden surface is as diverse as any exposed continent. The interplay between hidden mountains, valleys, and subglacial lakes creates a complex system. Water collects in basins, flows along valleys, lubricates ice sheets over mountains, and influences the stability of the entire ice sheet. The continent beneath the ice is dynamic, alive in its own way, shaped by millions of years of geological activity. The discovery of subglacial landscapes also raises questions about potential refuges for life. Microbes may inhabit isolated valleys, subglacial lakes, and geothermal regions, protected from surface extremes. These hidden environments could preserve ancient life forms, revealing evolutionary pathways not seen elsewhere. Antarctica's mountains and valleys are more than rock. They are laboratories of survival and resilience. Some of the deepest valleys contain sediment layers from pre-glacial periods, rocks eroded and transported by ancient rivers, minerals deposited over millions of years. Each layer is a chapter in Antarctica's long history, offering clues about climate, glaciation, and the possible presence of life during warmer epochs. The hidden mountains also have implications for understanding Earth's tectonics. Seismic studies reveal fault lines, uplifted formations, and evidence of ancient collisions. Antarctica's buried peaks may help reconstruct the positions of supercontinents, showing how continents drifted and collided over hundreds of millions of years. The Gamburtsevs and other ranges are keys to Earth's geological puzzle. In essence, Antarctica's hidden mountains and valleys are both scientific marvels and sources of mystery. They preserve the continent's history beneath ice, influence glaciers, support isolated ecosystems, and inspire questions about life in extreme environments. Each discovery reveals complexity, challenges assumptions, and expands our understanding of the frozen world. The hidden landscapes are silent witnesses, recording millennia of tectonic activity, glacial movements, and environmental change beneath the ice. Mountains rise, valleys plunge, lakes sit in shadowed basins. Each feature contributes to the story of Antarctica, a continent alive beneath its frozen veneer. And so the tale of hidden mountains and valleys is a story of discovery, preservation, and the extraordinary scale of Antarctica's hidden world, a world waiting for patient scientists, explorers, and dreamers to uncover its secrets. Antarctica is more than ice. It is a continent of hidden mountains, deep valleys, and untold history. Long before the ice sheets claimed Antarctica, life thrived across this southern continent. Forests stretched across valleys, rivers carved their paths through fertile plains, and animals, some unique to the region, roamed freely. Fossils discovered today tell a story of abundance, adaptation, and eventual loss. During the Mesozoic era, Antarctica was home to a variety of flora. Ferns, cycads, conifers, and primitive flowering plants grew in temperate climates. Fossilized leaves and pollen indicate lush ecosystems. Seasonal changes allowed periods of growth and dormancy. Rivers and lakes supported diverse life forms. Birds and small reptiles likely inhabited the forests, feeding, nesting, and migrating. Dinosaurs were among the continent's most prominent residents. Evidence from the Transantarctic mountains and other regions reveals the presence of herbivorous species, such as sauropodomorphs, grazing on abundant vegetation. Carnivorous theropods stalked prey, their footprints preserved in sedimentary layers. Fossils suggest a diversity of species. Some adapted to long periods of darkness during polar winters. Life was resilient, thriving in extreme seasonal conditions. Marine life was equally rich. Surrounding seas teemed with ammonites, mollusks, and primitive fish. Early marine reptiles, such as plesiosaurs and ichthyosaurs, hunted these waters. Fossilized remains indicate a complex food web, where life adapted to both land and sea. Antarctic oceans were far warmer than today, supporting ecosystems similar to those of modern temperate seas. As the continents drifted southward, Antarctica gradually cooled. The The movement of tectonic plates shifted ocean currents, altering heat distribution across the planet. Ice sheets began forming in coastal regions, slowly expanding inland. These changes forced species to adapt, migrate, or perish. Fossils provide a record of these transitions, showing both resilience and extinction. Plant life evolved to survive colder conditions. Conifers became more dominant, while ferns retreated to sheltered valleys. Pollen grains preserved in sediments allow scientists to reconstruct ancient climates. These microfossils reveal shifts in temperature, precipitation, and seasonal cycles. Antarctica was becoming less hospitable, yet pockets of life persisted. Animal fossils also reflect adaptation to cooling climates. Species became smaller or developed insulation to survive harsher conditions. Fossilized bones show changes in physiology, indicating long-term evolutionary responses. The fossil record is incomplete, yet it provides snapshots of life's ingenuity. Even as ice advanced, the fossil record also reveals extinction events. Many species disappeared as ice sheets expanded. Habitat loss, changes in food availability, and colder temperatures contributed to their demise. Fossils serve as both evidence and warning, documenting the vulnerability of life to environmental change. Antarctica's history illustrates resilience, but also the limits of adaptation. Subglacial fossils offer additional insight. Ice preserves not just ancient plants, but also microfauna, microorganisms. Pollen and spores trapped in ice cores reveal ecosystems long buried. These discoveries demonstrate the continent's dynamic history, cycles of growth and loss, and the extraordinary preservation power of ice. Volcanic activity occasionally reshaped landscapes. Eruptions created temporary refuges by melting localized ice. Nutrient-rich ash layers promoted plant growth. Fossilized deposits indicate that life persisted near geothermal areas. Volcanoes created isolated ecosystems, pockets where species could survive extreme cold. Antarctica's subglacial history is a testament to the interplay between geology and biology. The transition from life-rich land to frozen desert was gradual, over millions of years. Ice sheets expanded, covering valleys, rivers, and forests. Species either adapted to ice, migrated to other continents, or became extinct. Fossil records show this shift in stages, from lush ecosystems to cold-tolerant life, to the near absence of macroscopic terrestrial species. Modern science continues to uncover hidden life beneath ice. Microbes isolated from subglacial lakes may represent lineages that survived in refuges during the continent's freezing. These microorganisms are descendants of ancient life, carrying genetic information from an era long before the ice fully advanced. Antarctica's frozen depths preserve evolutionary history, offering a window into resilience over millions of years. Fossilized tracks are another source of evidence. Footprints of dinosaurs and early mammals, preserved in sedimentary rock beneath glaciers, provide clues about behavior, movement, and interaction. Some tracks indicate social behavior, hunting strategies, and adaptation to polar winters. These impressions freeze moments in time, capturing life as it once existed. Ice cores also reveal chemical signatures of ancient ecosystems. Carbon isotopes, pollen, and plant residues indicate seasonal growth and decay. Volcanic ash layers provide timestamps for environmental events. Combined, these records allow reconstruction of Antarctic life across millions of years, a narrative of thriving ecosystems gradually succumbing to the relentless advance of ice. The story of ancient life beneath ice also informs our understanding of climate change. Fossils provide evidence of how species responded to temperature shifts. Ice sheet growth and changes in habitat. Life persisted where possible, retreated when necessary. Antarctica is a laboratory for studying the interplay between biology and climate. Antarctica's fossil record extends beyond dinosaurs and plants. Early mammals, amphibians, and insects left traces. Some species were unique to the continent, having evolved in relative isolation. Their disappearance coincides with ice sheet expansion. indicating the powerful impact of environmental change on evolution. The continent's transition to a frozen desert was not uniform. Some coastal areas remained habitable longer than the interior. Subglacial valleys and geothermal zones may have hosted microecosystems. Fossil evidence suggests life persisted in these refuges. Isolated populations survived in these pockets, awaiting periods of warmer climate. And so Antarctica's ancient life beneath ice tells a story of adaptation, resilience, and loss. Fossils, ice cores, and sediment layers reveal ecosystems that thrived in a world very different from today, a land of forests, rivers, and abundant animals, gradually transformed by climate, tectonics, and ice sheet expansion. The frozen continent preserves these stories silently. Beneath kilometers of ice, each fossil, pollen grain, and microbial trace is a window into a past ecosystem. Antarctica's frozen deserts were once thriving landscapes, and understanding this history informs our knowledge of evolution, climate change, and the resilience of life. Antarctica's past life is a reminder that even the harshest environments once supported abundance, that ice and isolation do not erase history, merely conceal it. The continent beneath the ice remains a repository of ancient ecosystems, waiting for science to uncover its secrets. Antarctica is not only a continent of hidden mountains, valleys, and frozen lakes. It is also a land of strange and mysterious ice formations, towering ice cliffs, deep crevasses, flowing subglacial rivers, and patterns etched into the surface create a landscape both beautiful and enigmatic. These formations are not merely scenic, they reveal the dynamic power of ice and hint at processes unseen elsewhere on Earth. Ice cliffs and domes dominate much of the Antarctic interior. Gigantic walls of ice rise thousands of meters, shaped by wind, pressure, and temperature fluctuations. Some cliffs reveal layers of compressed snow, providing a chronological record of snowfall, dust deposition, and climate shifts. Each striation is a story, a frozen testament to Earth's changing environment. Crevasses, deep fractures in the ice, are another remarkable feature. Some span hundreds of meters in length, plunging tens of meters deep, formed as glaciers move and flex. These fissures expose ancient ice, layers compacted over millennia. Scientists use them to study ice flow dynamics. Trapped air bubbles reveal past atmospheric composition. Crevasses are both a hazard for explorers and windows into history. Antarctica's ice streams are rivers of solid ice, flowing slowly toward the sea, shaped by gravity. Underlying topography and temperature gradients, ice streams carve valleys, erode bedrock, and transport sediments. They are fast-moving compared to surrounding ice, sometimes dozens of meters per year, acting as conveyor belts of ice, draining interior regions, and influencing global sea levels. Subglacial rivers add further intrigue. Beneath kilometers of ice, liquid water flows, creating channels that shape the ice from below. These rivers lubricate ice sheets, enabling faster movement over mountains and valleys. They carve tunnels and deposit sediments, some of which may contain microbial life. These hidden waterways remain largely inaccessible, yet they play a crucial role in Antarctica's ice dynamics. Unusual ice formations sometimes take the form of sastrugi, wind-sculpted ridges, sharp, jagged patterns formed by persistent Katabatic winds. These features demonstrate the interaction between ice, wind, and temperature. They affect snow accumulation and ice sheet behavior. Studying sastrugi helps scientists understand the movement of surface ice and the forces shaping the continent's frozen exterior. Ice caves provide another fascinating feature, formed by geothermal heat, subglacial rivers, or volcanic activity. These caves are dynamic, changing shape as ice melts, refreezes, or collapses. Inside, ice stalactites, pillars, and intricate formations reveal processes occurring over centuries. Some caves are so stable that they preserve ancient air bubbles, microorganisms, even fragments of plant material. Antarctica's ice caves are natural laboratories, revealing microcosms of frozen history. The phenomenon of blue ice areas is equally remarkable. Wind scours away snow, exposing dense ice layers. These areas reflect light differently, appear deep blue, and often contain meteorites, preserved debris, and other materials from space. Blue ice zones are critical for studying past climate, meteor impacts, and ice dynamics. They are natural windows into Earth's frozen archives. Some ice formations appear almost geometric, unusual ridges, circular depressions, or linear patterns formed through natural ice flow, pressure, and melting. Yet they occasionally inspire speculation. Could some features reflect hidden subglacial structures or ancient events now preserved beneath ice sheets? While no evidence exists for human construction, such anomalies captivate scientists and theorists alike. Antarctica also hosts ice rises and domes, elevated areas where ice is thicker or slower moving, influenced by underlying bedrock. These formations can stabilize surrounding glaciers, slowing ice flow and preserving older ice layers. Ice cores extracted from domes provide uninterrupted climate records, sometimes stretching back hundreds of thousands of years. Each dome is a repository of ancient environmental data. The interaction of ice with geothermal activity creates further mysteries. Hot spots beneath the ice sheet melt localized areas, forming lakes, tunnels, and channels. These features affect ice flow, create habitats for microbial life, and may influence large-scale ice dynamics. Antarctic ice is alive, moving, shifting, and responding to forces from below and above. Crevasses and hidden ice cliffs sometimes expose ancient frozen landscapes. Sediments, rocks, and air bubbles trapped within reveal millennia of environmental change, explosions of dust from volcanic eruptions, periods of warming and cooling, and atmospheric composition are all recorded. Scientists study these formations to reconstruct Earth's climate history. Antarctica's ice is both archive and sculptor, preserving the past while continuously shaping the present. Subglacial lakes interact with overlying ice. Meltwater lubricates ice sheets, allows movement, and occasionally causes sudden ice collapses. These interactions produce chaotic crevasing, unique surface patterns, and anomalies visible in satellite imagery. The hidden interplay between water and ice creates unpredictable landscapes, fascinating scientists and explorers alike. The dynamics of ice also produce ice tongues and glaciers extending to the sea. Some glaciers flow continuously for hundreds of kilometers, carving fjords, depositing sediment, and forming icebergs that drift into the Southern Ocean. These formations are key to understanding Antarctica's role in global climate and sea level regulation. They are dramatic reminders of ice as a moving, living force. Antarctica's ice formations are also repositories of extraterrestrial material. Meteorites preserved on blue ice areas provide insights into the solar system. Trapped debris from space offers a glimpse of ancient cosmic events. The ice is a natural collector, protecting and concentrating materials over millennia. Antarctica's frozen surface is a laboratory for both terrestrial and extraterrestrial history. Some formations, like penitents, rise like jagged spires, formed by sublimation of snow in cold, dry conditions. These spiky structures, shaped by sunlight and wind, illustrate the extremes of Antarctic microclimates. Studying them provides clues about ice ablation, solar energy impact, and local weather conditions. Every ice formation is evidence of ongoing environmental processes. Ice formations also influence scientific logistics. Crevasses, ridges, and hidden rivers pose hazards, yet they also guide exploration. Blue ice zones provide natural runways for aircraft. Stable ice domes offer access for drilling and research stations. The ice itself shapes human activity. Antarctica's frozen landscape is both obstacle and enabler. The mystery of Antarctica's ice formations continues to inspire speculation. Some theorists link unusual formations to hidden geological structures or ancient catastrophic events. While most features are naturally occurring, their scale and complexity remind us of the continent's power and ancient history. Ice is not passive. It is a record, a sculptor, and a storyteller. And so, the story of Antarctica's mysterious ice formations is one of beauty, complexity, and hidden power, from towering cliffs to flowing ice streams, from subglacial rivers to blue ice zones. Each formation is part of a dynamic system, revealing processes that shape not only Antarctica, but the global environment. Ice is both frozen history and living landscape, a silent witness to Earth's past and present. Antarctica's ice sheets are more than frozen landscapes. They are vast archives of Earth's history, containing layers of snow, ice, and trapped air that record climate, atmospheric composition, and environmental events over hundreds of thousands of years. Each meter of ice holds a story, waiting for patient scientists to decode it. Ice cores are the primary tools for unlocking these secrets. Cylinders of ice drilled from depths of several kilometers reveal successive layers deposited year after year. Each layer preserves not only snow, but also dust, volcanic ash, pollen, even microscopic life. Air bubbles trapped in the ice capture ancient atmospheres, allowing researchers to measure greenhouse gases, oxygen, and nitrogen levels from long ago. The study of ice cores has revolutionized understanding of climate change. By analyzing isotopic ratios of oxygen and hydrogen in the ice, scientists can infer past temperatures. Seasonal variations reveal periods of warmth and cold. Decades, centuries, and millennia of climate cycles are recorded. Antarctica's frozen depths provide one of the clearest windows into Earth's climate history. Volcanic eruptions leave distinct markers in ice cores. Layers of ash and sulfur compounds indicate timing and magnitude. These eruptions affected global climate, triggered cooling periods, altered ecosystems, and occasionally caused mass extinctions elsewhere on Earth. Antarctica preserves a precise record, enabling reconstruction of geological and environmental events with remarkable accuracy. Ice cores also contain microscopic organisms, bacteria, fungi, and algae trapped during snowfall. These microbes reveal resilience in extreme conditions. Their survival strategies may inform understanding of life on other planets. Ice is not just a record of atmosphere, it is a repository of biology. Ancient DNA fragments, spores, and microorganisms provide insight into ecosystems long vanished. Dust particles embedded in ice reveal information about distant regions. Winds transported material from continents thousands of kilometers away. Desert dust, volcanic ash, and sea salt reveal past wind patterns. Antarctic ice cores function as natural meteorological records, recording climate variability, storms, and even ancient storm tracks. Analysis of chemical composition uncovers fluctuations in greenhouse gases. Carbon dioxide, methane, and nitrous oxide levels vary through time. These fluctuations correlate with glacial and interglacial periods. Ice cores reveal the relationship between greenhouse gases, temperature, and sea level. Antarctica is a laboratory for understanding Earth's climate system. Some ice cores contain evidence of rare catastrophic events, meteor impacts, sudden volcanic eruptions, and abrupt climate anomalies leave distinct chemical or physical signatures. Traces of these events preserved for tens of thousands of years provide insights into the scale and impact of ancient disasters. Antarctica preserves this history with unparalleled fidelity. Beyond the atmosphere, ice cores preserve evidence of ancient ecosystems. Pollen, plant fragments, and microbial remnants provide clues to flora and fauna. The transition from a fertile continent to frozen desert is recorded in these layers. Scientists can track when forests disappeared, when ice sheets expanded, and when isolated pockets of life persisted. Antarctica is a living record of evolutionary history. The depth of ice correlates with age. Deep cores near the center of the continent can reach 800,000 years old. Every meter corresponds to decades or centuries. Sampling this ice is painstaking. Extreme cold, remote locations, and fragile equipment complicate research. Yet the reward is access to a continuous record of Earth's environment. Technological advances allow even greater precision, mass spectrometry, DNA sequencing, and isotopic analysis reveal detailed information about past conditions. Ice preserves chemical fingerprints of ancient air, volcanic eruptions, and biological material. Even subtle variations in impurity concentrations provide insight into environmental changes. Antarctica is a time machine frozen in layers of ice. Ice cores also illuminate interactions between Antarctica and global systems. Ocean currents, atmospheric circulation, and solar radiation influence snow accumulation and ice composition. Conversely, changes in Antarctic ice affect global sea levels, climate, and ecosystems. Studying ice cores reveals the interconnectivity of Earth systems over geological time. Scientists have discovered abrupt climate changes in ice records, rapid warming or cooling events, sometimes occurring over decades, are preserved. These anomalies challenge assumptions about gradual climate change. Antarctica's ice offers evidence that the planet is capable of sudden transformations. Understanding these events helps predict future climate trends. Subglacial lakes, hidden valleys, and ice cores together create a complete picture. Life persists beneath the ice. Microbes thrive in liquid water trapped under frozen layers. Sediments contain fossilized remains of ancient plants and animals. Ice cores bridge the gap between biology, geology, and climate science. Antarctica preserves a multidimensional archive. The preservation of ancient air and life in ice raises tantalizing possibilities. Could ice cores contain evidence of long-lost ecosystems, microbial lineages, or chemical markers of past biological activity, previously unknown species preserved for millennia? Each discovery offers clues to Earth's resilience and adaptability. Antarctica's ice is a silent witness to life's persistence. Ice cores also document human influence, albeit in recent centuries. Industrial pollutants, lead, and other contaminants appear in the most recent layers. This provides context for understanding anthropogenic climate change. Antarctica preserves a record of both natural and human-driven environmental transformations. The contrast between past and present is stark. The study of ice cores requires meticulous care. Contamination from modern microbes or chemicals must be avoided. Researchers sterilize equipment, work in controlled environments, and carefully transport samples. Only through precision and patience can the secrets of Antarctica's ice be unlocked. Through ice core research, humanity gains a window into deep time, into the rhythms of Earth's climate, the rise and fall of ecosystems, the impact of catastrophes, and the persistence of life in extreme conditions. Antarctica's frozen secrets illuminate not just the past, but the potential future of our planet. And so, the story of secrets buried in the ice is one of patience, discovery, and revelation. Every meter drilled, every bubble analyzed, every microscopic fragment examined, adds to our understanding of Earth's dynamic history. Antarctica is more than ice, it is a living archive, preserving climate, life, and environmental history for those who seek its truths. Antarctica's interior is a frozen expanse of ice and rock, but its edges tell a different story here. The ice meets the Southern Ocean, forming vast ice shelves, massive glaciers, and dramatic coastal formations. The interface between ice and sea is dynamic, constantly changing. These margins are critical to understanding the continent's stability, and their interactions influence global sea levels. Ice shelves are floating extensions of glaciers. They can extend hundreds of kilometers into the ocean, acting as buffers. They slow the flow of ice from the interior to the sea. The Ross Ice Shelf, one of the largest, covers over 500,000 square kilometers. Its thickness exceeds 600 meters in some regions. Beneath its surface, the ice is sculpted by currents, tides, and temperature gradients. Ice shelves are both fragile and immense, majestic in scale, yet sensitive to environmental change. The edges of these ice shelves are riddled with crevasses and rifts, formed by stress, tidal movement, and ice flow. These fractures can propagate for kilometers. Icebergs calve from these rifts, breaking off and drifting into the Southern Ocean. Calving is a natural part of ice shelf life, yet its frequency and magnitude have increased with warming oceans. Each iceberg carries a story: ancient ice, trapped gases and microbial life into the ocean. Glaciers feeding ice shelves are equally fascinating. Pine Island Glacier and Thwaites Glacier, for instance, flow rapidly, transporting ice from the interior to the coast. Their grounding lines, where ice begins to float, are highly sensitive to changes in ocean temperature. Even slight warming can accelerate ice flow, contributing to sea level rise. Antarctica's edges are where the frozen continent most directly interacts with the global climate system. The ocean itself shapes ice shelves and coastal glaciers. Warm water circulating beneath ice shelves melts them from below, creating channels and cavities. This basal melting influences ice shelf stability and can trigger accelerated glacier movement. Subsurface currents, tides, and ocean temperature anomalies combine to create a constantly shifting interface. A complex dance between ice and ocean unfolds. Hidden beneath the surface, coastal topography affects how ice shelves behave. Peninsulas, ridges, and valleys beneath the ice influence flow. Narrow channels accelerate ice streams, while wider basins stabilize ice. Mapping these features requires radar, seismic surveys, and satellite imagery. Understanding the hidden landscape beneath ice shelves is critical for predicting future changes. Antarctica's edges are both visible and concealed, dynamic yet secretive. Some ice shelves experience rapid disintegration events. Sudden collapses occur when rifts propagate through weakened ice. Warming temperatures, ocean melt, and structural weaknesses contribute. The breakup of the Larsen B ice shelf in 2002 is a stark example. Over 3,000 square kilometers of ice disintegrated in weeks. Satellites captured the dramatic process, revealing the vulnerability of these frozen extensions and the speed with which nature can reshape them. Ice shelves also host subglacial lakes near their grounding lines. Meltwater lubricates ice flow, influences stability, and supports microbial ecosystems in dark, pressurized environments. Life beneath the ice persists even at the margins. Antarctica's edge is both a frontier of glaciology and a refuge for extremophiles. Scientists study these systems to understand how ice, water, and life interact. The interaction between ice and ocean creates unique surface features. Melt ponds, ridges, and crevasses sculpt the ice. Brine channels in sea ice concentrate salts, influencing local microbial communities. Ice cliffs form where floating ice meets open water. These cliffs can reach hundreds of meters in height. Some have collapsed catastrophically, sending ice into the ocean. Antarctica's coastal ice is both beautiful and perilous. Ice-ocean interactions also affect global systems. Freshwater from melting ice shelves enters the Southern Ocean, altering salinity, density, and circulation patterns. The Antarctic circumpolar current responds to these changes, influencing weather, climate, and marine ecosystems around the world. Antarctica's edges are thus central not only to local dynamics, but to planetary climate systems. The formation of icebergs is a dramatic feature of Antarctica's edges. Large chunks of ice detach from shelves, floating silently into the Southern Ocean. These icebergs can drift for years, melting slowly, influencing ocean currents and ecosystems. Each iceberg carries a frozen record: air bubbles, sediments, and microscopic life, a messenger from the frozen continent. Tides and seasonal variations shape ice shelves as well. Summer meltwater seeps into crevasses, refreezing during winter, creating a cycle of stress, fracture, and movement. Ice shelves respond to tidal flexing, bending and cracking. These processes, though gradual, have enormous cumulative effects. Antarctica's edges are constantly evolving, a frozen margin in perpetual motion. Ice shelves also record history. Layers of snow and ice capture past climate conditions. Dust, volcanic ash, and biological material provide a timeline. Scientists extract cores near the edges to study changes over centuries. Understanding ice shelf history is essential for predicting future behavior under climate change. Antarctica's frozen margins are living archives of Earth's environmental history. The edges are also habitats seals, penguins, and seabirds inhabit regions near ice shelves. Open water and ice provide feeding and breeding grounds. Marine productivity is influenced by freshwater influx from melting ice. Life at the edge adapts to extreme cold, seasonal darkness, and dynamic ice conditions. Antarctica's edges are where ice and life meet. Subglacial rivers beneath coastal glaciers play a critical role, channeling meltwater toward the sea, lubricating ice flow, and connecting interior lakes with the ocean. These hidden waterways are essential to understanding ice dynamics. They reveal the interconnectedness of Antarctic ice. Beneath the surface, Antarctica's edges are a threshold between frozen interior and living ocean. The melting of ice shelves has global consequences. As ice is lost, glaciers accelerate, contributing to rising sea levels. Understanding the processes at the edge is critical. Models rely on precise measurements of ice thickness, melt rates, and grounding line stability. Antarctica's edge is the frontline of climate change, a place where the frozen continent responds to a warming planet. And so, the edge of the continent is a realm of power, mystery, and constant change. Ice shelves, glaciers, and subglacial rivers interact with the ocean, shaping both Antarctica and the world beyond. These margins are not static, they are dynamic, alive, recording past events, influencing present processes, and warning of future shifts. Antarctica's edges are the living frontier, where ice meets sea and history meets the present. Antarctica is a land of ice, mountains, and hidden valleys, but it is also defined by its wind, powerful, relentless, and shaping every aspect of the frozen continent. The Katabatic winds, descending from the high interior toward the coast, are the most dramatic. These cold, dense winds accelerate under gravity, reaching speeds that can exceed 300 kilometers per hour. They sculpt the landscape, influence ice dynamics, and challenge every explorer who dares traverse the continent. Katabatic winds form when cold, dense air accumulates over the high interior plateaus. Gravity pulls this air downward. Channels between mountains accelerate flow. As the winds descend, they compress and warm slightly, creating a powerful force that sweeps across ice sheets. Their influence is visible in the snow, carving sastrugi, eroding surfaces, and shaping crevasses. The winds are both artist and sculptor, continuously modifying Antarctica's frozen canvas. These winds affect the formation of ice structures. Snow is abraded, transported and redeposited, ridges form, valleys deepen. Exposed surfaces reflect light differently, influencing melting patterns. Katabatic winds are a key factor in the formation of blue ice areas. Snow is removed, leaving dense ice layers exposed. These zones reveal ancient ice meteorites and dust from distant continents. Winds thus serve as both creator and revealer. The winds also influence the behavior of glaciers. Surface stress from fast-moving winds accelerates sublimation. The loss of snow and ice affects ice density, altering flow patterns over hidden valleys and mountains. Wind-driven snow redistribution contributes to ice sheet dynamics. Antarctica's frozen landscape is constantly reshaped by the invisible hand of air. Wind patterns also affect climate locally and globally. Cold air masses moving toward the coast interact with ocean currents, bringing extreme temperatures to coastal regions, influencing sea ice formation and melt. Katabatic winds can trigger storms, creating blizzards that reduce visibility to zero. These winds are central to Antarctica's harsh environment, controlling both ice behavior and weather conditions. The speed and power of the winds are legendary. Explorers recount how katabatic gusts can knock people down, bury tents, and sweep away equipment. The combination of extreme cold and high velocity creates wind chills beyond comprehension. Even modern scientific stations must design buildings and instruments to withstand these forces. Antarctica's winds are both sculptor and adversary, demanding respect. Katabatic winds also influence life. Microbial life in snow and ice must survive exposure. Penguins and seals adapt by timing their movements. Birds use wind patterns to aid flight. Even ocean currents are affected. Wind-driven mixing of surface waters influences nutrient distribution. Antarctica's winds are thus a link between ice, life, and the ocean. The winds create unique phenomena. Diamond dust, tiny ice crystals suspended in the air, forms in extreme cold. Sunlight refracts through these crystals, creating halos, sun dogs, and other optical effects. These displays are brief, ephemeral, yet demonstrate the interplay of light, air, and ice. Antarctica's winds are both destructive and magical, shaping what can be seen and felt. The Katabatic winds also reveal hidden terrain, as snow is blown away from peaks and valleys. Ice layers and subglacial formations are exposed. Satellites capture these windswept zones, offering scientists clues to underlying mountains and lakes. Winds thus contribute to discovery, uncovering the continent's secrets without human intervention. Wind-driven erosion is another critical process. Ice cliffs and exposed ridges are sculpted over millennia. Fine particles of snow are carried across the surface, abrading rocks, smoothing ice, and influencing sediment transport. Katabatic winds are a geological agent, silently working over thousands of years, shaping Antarctica as much as ice itself. Seasonal variations influence wind strength. During winter, the cold interior intensifies katabatic flow. Summer brings slightly warmer temperatures and occasionally shifts in direction. These cycles affect snow accumulation, ice flow, and weather patterns. Understanding Antarctic winds is crucial for climate modeling and predicting changes in ice stability. The winds also amplify the continent's isolation. Communication, travel, and logistics are affected by sudden gusts and blizzards. Research stations must plan for extreme conditions. Helicopters and vehicles navigate carefully. The human experience of Antarctica is defined as much by the wind as by the ice. Katabatic gusts are an omnipresent force, shaping both natural and human activity. Wind patterns interact with topography. Mountain ranges funnel winds, accelerating them in narrow passes. Valleys channel airflow, creating localized storms. Coastal regions experience a mixture of katabatic winds and oceanic influence. The complexity of these interactions makes predicting wind behavior challenging. Antarctica's air movements are a complex system, intertwined with ice, topography, and ocean. The winds also play a role in energy balance. By removing snow and exposing dark ice or sediment layers, they affect albedo. This influences melting patterns, ice sheet stability, and local climate feedbacks. Katabatic winds are thus a subtle yet powerful factor in Antarctica's environmental dynamics. Life at the edge of these winds must be hardy. Microbes survive in snow grains. Birds time flights with wind direction. Seals adjust hunting patterns. Even vegetation in peripheral regions is influenced. The winds are not just a physical force, they shape ecosystems, adaptation, and survival strategies. Some of the most extreme winds occur near coastal cliffs and ice rises. Gusts can tear through temporary research stations, scour ice surfaces, and create spectacular snowdrifts. They are reminders that Antarctica is a land of extremes. The continent's frozen interior may be quiet, but the winds ensure that no place is ever entirely still. And so, the story of Antarctica's winds is one of power, influence, and subtlety, from shaping ice formations to affecting climate, glaciers, and life. Katabatic winds are a constant presence, silent sculptors, relentless forces, and essential components of the frozen continent. Understanding them is crucial to understanding Antarctica itself. Beneath Antarctica's thick ice sheets lies a hidden world, a labyrinth of lakes, rivers, and waterways, shielded from sunlight for millions of years. These subglacial waters are among the most mysterious and extreme environments on Earth, providing insight into how life can persist in isolation and how Earth's climate and geology interact beneath the ice. The most famous of these hidden bodies is Lake Vostok, buried under more than 4 kilometers of ice. It is one of the largest subglacial lakes in the world, roughly the size of Lake Ontario, and isolated from the surface for at least 15 million years. The pressure and temperature of the overlying ice maintain a liquid state. Despite the extreme cold, Lake Vostok is a time capsule, preserving conditions from an ancient Earth. Other subglacial lakes, such as Lake Whillans, Lake Mercer, and Lake Ellsworth, form networks connected by subglacial rivers. Water flows slowly, moving kilometers per year beneath the ice. These rivers lubricate the ice above, influencing glacier movement and ice sheet dynamics. Subglacial hydrology is complex, a hidden system that shapes both the ice and the underlying bedrock. Scientific drilling has revealed remarkable properties of these lakes. Water chemistry differs from surface lakes. Nutrient concentrations are low, oxygen levels are often limited. Yet microbial life has been discovered. Bacteria, archaea, and other microorganisms thrive in total darkness, drawing energy from chemical reactions rather than sunlight. Antarctica's subglacial lakes are living laboratories, demonstrating the resilience of life in extreme isolation. The sediment beneath these lakes also holds ancient clues. Layers of mud, silt, and rock contain fossils and chemical markers, indicating past climates, glacial advances and retreats, and even possible remnants of prehistoric ecosystems. Sediment cores may reveal organisms that survived long before the ice fully advanced, preserving history inaccessible elsewhere on the planet. Subglacial rivers connect these lakes. Channels carved through bedrock and ice create hidden aquatic highways. Water flow is driven by pressure gradients and melting at the ice base. Movement of water under kilometers of ice is slow, yet persistent. Over time, these rivers reshape the underlying topography, creating channels, caverns, and pockets where life may survive. These hidden waters also influence the overlying ice. Subglacial lakes act as lubricants. Ice above moves more rapidly when water pressure increases. This interaction can destabilize glaciers, potentially contributing to iceberg calving at the edges. The Antarctic ice sheet is a system where water beneath controls ice above, unseen forces shaping global sea levels. The extreme conditions in subglacial lakes make them challenging to study. Scientists use sterile drilling techniques to avoid contamination. Remote sensors and autonomous vehicles probe the lakes. Water samples are analyzed for microbial life, chemical composition, and isotopes. Each discovery adds to our understanding of life under extreme isolation and how the planet's systems interact beneath the ice. Some subglacial lakes may have been refuges for life during glacial maxima, isolated from surface events. They could harbor lineages of microorganisms separated from the rest of the planet for millions of years. Studying these life forms helps us understand evolution in extreme environments and the possibilities for life on other worlds. Antarctica is an analog for icy moons such as Europa or Enceladus, where liquid water exists beneath frozen shells. The chemical environment of these lakes is fascinating. Minerals leached from bedrock interact with water, creating energy sources for microbes. Nutrients are recycled slowly. Life persists in balance with extreme scarcity. These ecosystems demonstrate remarkable adaptation, showing that even under kilometers of ice, life finds a way. The physical structure of subglacial lakes also varies. Some are shallow basins, others are deep troughs. Some lakes are connected, forming networks spanning hundreds of kilometers. Flow dynamics depend on pressure, temperature, and ice sheet topography. Understanding these dynamics is key to predicting ice sheet behavior under changing climate conditions. Subglacial lakes are also influenced by geothermal heat. Heat from Earth's interior melts the base of the ice sheet, maintaining liquid water and sustaining ecosystems. Localized geothermal zones create microhabitats, life clusters near nutrient sources. Antarctica's hidden aquatic systems are islands of survival beneath kilometers of ice. Exploration of these lakes has yielded surprises. Microbial diversity is greater than expected. DNA sequencing reveals unique lineages. Some microbes metabolize iron, sulfur, or methane. Others survive in extreme pressure and cold. These discoveries redefine the limits of life, demonstrating that isolation does not equate to sterility. The discovery of subglacial rivers connecting lakes also raises questions about water circulation. How fast does water flow, and how does it interact with the ice above? Can chemical signals or organisms travel across the continent beneath the ice? These hidden networks may be crucial to understanding both ice stability and ancient ecological continuity. Antarctica's subglacial lakes also act as archives of past climate. Water and sediments preserve information about temperature, precipitation, and ice sheet dynamics. Volcanic ash trapped in lake sediments can be dated, providing a timeline for glacial events. These lakes are repositories of Earth's frozen memory. The isolation of these lakes may have allowed life to evolve independently. Microbial ecosystems may have remained unchanged for millions of years. Genetic studies reveal adaptations unseen elsewhere. Life in these lakes provides insights into resilience, evolution, and survival under extreme conditions. Subglacial aquatic systems also have implications for modern climate change. As ice sheets melt from below, water flow may increase, lubricating glaciers and accelerating ice movement. Understanding these hidden lakes is crucial for modeling future sea level rise. Antarctica's hidden waters connect past, present, and future. The mystery of subglacial lakes captivates scientists and the public alike, hidden from view, isolated beneath kilometers of ice. Yet teeming with microscopic life and preserving ancient history, Antarctica is a continent of extremes, where darkness, pressure, and isolation create a unique laboratory for science. And so, the story of subglacial lakes and rivers is one of hidden life resilience, and the interplay between ice, water, and geology. Beneath the frozen surface, ecosystems survive, ancient climates are preserved, and the continent's secrets await discovery. Antarctica's hidden waters are a testament to the endurance of life and the persistence of history beneath the ice. Beneath Antarctica's vast ice sheets lies a landscape almost as dramatic as the surface of other continents. Yet this world remains largely invisible. Covered by kilometers of ice, Antarctica conceals towering mountains, deep valleys, and sprawling plateaus. Subglacial topography shapes ice flow, influences climate, and preserves evidence of the continent's geological history. The hidden terrain is both sculptor and archive, silently dictating how ice moves and how the continent evolves. The Gamburtsev Mountains are among the most remarkable discoveries beneath the ice, discovered by radar in the 1950s and mapped in detail decades later. These mountains are comparable in size to the European Alps. Peaks rise up to 3,000 meters, yet no human has ever seen them. Snow and ice blanket the range, hiding jagged cliffs and valleys. The Gamburtsevs are a frozen secret, a reminder that Antarctica is not simply a flat, featureless expanse. These mountains influence ice sheet dynamics profoundly. Ice flows over and around the ranges, forming deep crevasses, ridges, and stress zones. Subglacial valleys guide glaciers, accelerating flow in some regions, slowing it in others. The underlying topography is crucial for predicting ice sheet behavior. Understanding hidden mountains is essential to modeling sea level rise and ice stability. Other mountain ranges lie beneath the Antarctic ice. The Transantarctic Mountains stretch over 3,500 kilometers, dividing East and West Antarctica. These mountains are partially exposed in some regions, yet much of the range is hidden beneath ice. Valleys carved by glaciers contain ancient sediments and rocks, recording tectonic shifts, climate changes, and the movement of ice over millions of years. Subglacial valleys often contain lakes and rivers. These waterways flow beneath ice, carving channels in bedrock. Their presence affects ice stability, lubricating movement, and influencing patterns of calving at the margins. Hidden rivers may connect lakes across vast distances, creating networks that shape the continent from beneath. The topography is a map of past and present processes. Invisible but powerful, radar and satellite imaging have revolutionized understanding of subglacial features. Ice-penetrating radar reveals mountain peaks, valleys and ridges. Gravity measurements infer bedrock density. Combining these techniques produces detailed maps of the hidden continent. Scientists can now visualize ice thickness, subglacial lakes, and even ancient riverbeds. Antarctica's underground landscape is slowly emerging from obscurity. The interaction between ice and topography creates dynamic stress zones. Mountains slow ice flow, causing compression, forming crevasses and fractures. Valleys channel ice streams, accelerating movement. These interactions create a complex, ever-changing environment beneath the ice. Subglacial topography is a silent engineer shaping Antarctica's frozen surface and influencing its global impact. Ancient erosion and sedimentation patterns are preserved in hidden valleys, rocks exposed beneath the ice record tectonic history. Fossils embedded in subglacial sediments reveal life that existed before Antarctica became frozen. These geological features offer insight into ancient climates. The continent was once temperate, covered in forests, lakes, and rivers. Subglacial mountains and valleys are the guardians of this deep history. Subglacial volcanoes also contribute to hidden topography. Geothermal heat influences ice flow, melting localized areas beneath the ice, creating subglacial lakes, tunnels, and dynamic ice conditions. Some volcanoes remain active, others dormant. Yet even dormant features affect ice movement. Geology beneath the ice interacts with surface processes, shaping Antarctica in profound ways. The existence of these mountains challenges assumptions about continental formation. Antarctica is not simply a flat ice desert. Its hidden ranges reveal tectonic activity, rift valleys and uplift events. East and West Antarctica have distinct geologies. Ice conceals complex interactions between crust, mantle, and surface processes. Understanding these hidden features is essential to understanding the continent as a whole. Subglacial mountains also influence climate. They direct Katabatic winds, affect snow accumulation, and create microclimates beneath the ice. Valleys may trap cold air, while ridges redirect flow. These subtle effects influence ice thickness, melting, and the preservation of ancient layers. Antarctica's hidden topography shapes not just the ice, but the conditions within it. Hidden valleys contain frozen records of past glacial activity. Moraines, sediments, and rock deposits reveal cycles of advance and retreat. Glacial scouring carved deep troughs. Deposits indicate periods of melting, stability, and renewal. These features are essential for reconstructing the continent's glacial history. They reveal how ice has sculpted the land over millions of years. Life may also persist in subglacial valleys. Microbial ecosystems in water trapped beneath ice are influenced by surrounding bedrock and topography. Sediments provide nutrients. Pressure and geothermal heat create microhabitats. These hidden valleys may host life that has been isolated for millions of years. Antarctica conceals both geology and biology beneath the ice. The interplay between mountains, valleys, and ice creates stress zones critical to predicting ice sheet collapse. Areas where ice is thinner over valleys may be prone to accelerated movement. Peaks can stabilize ice. These factors must be considered when modeling the response of Antarctic ice to climate change. Hidden topography dictates much of the continent's behavior. Exploration continues. Autonomous vehicles, radar surveys, and satellite monitoring gradually uncover the secrets of subglacial terrain. Each discovery provides new understanding. New mountains, valleys, and ridges are mapped, ancient riverbeds are identified, and subglacial lakes are connected to broader networks. Antarctica's underground landscape is slowly revealing itself. The hidden mountains and valleys also tell a story of resilience. Ice flows over obstacles. Life persists in isolated pockets. Ancient sediments survive beneath kilometers of ice. The continent is dynamic yet preserved. Antarctica is both a frozen frontier and a living archive of Earth's history. And so, the story of hidden mountains and valleys is one of concealment and revelation. Subglacial topography shapes ice flow, preserves geological and biological history, and holds secrets of Earth's deep past. Antarctica's frozen surface conceals a dynamic world beneath, a world that continues to evolve, silently shaping the present and preserving the past. Antarctica is more than ice, more than a remote continent at the bottom of the world. It is a keystone in Earth's history, a witness to tectonic shifts, climatic transformations, and the evolution of life. Its frozen expanses preserve records that span hundreds of millions of years. From the supercontinent Gondwana to the present day, Antarctica has shaped and been shaped by the forces of our planet. The continent's geological history stretches back over 500 million years. Antarctica was once part of the supercontinent Gondwana, connected to what are now Africa, South America, Australia, and India. Fossils found in Antarctica reveal temperate forests, flowing rivers, and diverse ecosystems. Ferns, mosses, and ancient reptiles thrived. The climate was warm, ice was absent, and life flourished. These discoveries remind us that Antarctica was once central to Earth's biodiversity. Tectonic activity has dramatically transformed the continent. Mountain building, rift valleys, and volcanic activity created hidden ranges and subglacial lakes. The Gamburtsev Mountains, buried beneath ice, bear witness to tectonic forces. East and West Antarctica have distinct geological histories. Their separation influenced ice sheet development and continental climate patterns. Antarctica's geology provides insight into the formation and breakup of continents over deep time. Antarctica's ice sheets are central to understanding global climate history. Ice cores reveal atmospheric composition, temperature fluctuations, and greenhouse gas levels over hundreds of thousands of years. Layers of snow and ice record volcanic eruptions, meteor impacts, and abrupt climate changes. The frozen continent preserves a timeline, a living archive, allowing scientists to reconstruct Earth's climate and understand natural cycles. The continent's influence extends far beyond its borders. Ice sheets regulate sea levels. Ice shelf collapse can accelerate glacier flow, introducing freshwater into the Southern Ocean. This affects ocean currents, weather patterns, and climate globally. Antarctica's frozen mass is a regulator, a stabilizer of planetary systems. Its role in the Earth's hydrological cycle is indispensable. Antarctica also preserves evidence of past ecosystems. Fossils, pollen, and microbial life provide a window into prehistoric environments. Subglacial lakes and rivers conceal life isolated for millions of years. Sediments reveal ancient flora and fauna. Ice cores capture atmospheric chemistry. The continent is both laboratory and archive, revealing interactions between life, climate, and geology. The continent has played a critical role in understanding glaciation. The expansion and retreat of Antarctic ice sheets influenced global climate cycles. Sea levels rose and fell with glacial maxima and minima. Antarctica's ice sheets are sensitive indicators, recording natural variability and human-induced change. Studying them informs predictions for the future. Antarctica's subglacial lakes, rivers, and topography offer insight into Earth's hidden systems. Water beneath the ice influences ice movement, nutrient cycles, and microbial ecosystems. Geothermal activity affects basal melting. Together, these features connect geology, hydrology, and biology. Antarctica is a multidimensional archive, preserving interactions across Earth's systems. The continent has also been a focal point for understanding life in extreme conditions. Microbes in subglacial lakes, organisms surviving Katabatic winds, life enduring in ice cores and snow layers. These adaptations provide clues for astrobiology. Antarctica serves as an analog for icy moons and planets, where life may exist beneath frozen surfaces. Its hidden worlds teach resilience, persistence, and adaptability. Antarctica's role in sea level regulation cannot be overstated. The loss of ice from glaciers and shelves contributes to rising oceans. Coastal regions worldwide are affected. Understanding ice dynamics, hidden rivers, and subglacial lakes is crucial. The continent's frozen mass is intimately connected to human societies far from the polar regions. Its history is intertwined with the future of our planet. The continent has also shaped atmospheric circulation. The polar vortex, Katabatic winds, and ice-ocean interactions influence global weather. Antarctica's climate systems interact with mid-latitude patterns, shaping storms, precipitation, and ocean currents. Studying these interactions allows better forecasting. Antarctica is not isolated. It is a driver in Earth's climate machinery. Volcanic activity beneath Antarctica has also impacted its history. Geothermal heat shapes ice flow and creates habitats for subglacial life. Past eruptions left traces in ice cores and sediments. Some eruptions influenced regional climate. Others may have contributed to glacial melt events. Antarctica's geology and volcanism are intertwined with ice and life. The continent's role in preserving deep time cannot be overstated. Ice sheets act as time capsules, capturing air bubbles, dust, pollen, volcanic ash. Each layer tells a story. Each meter drilled provides insight into millennia of Earth's environmental changes. Antarctica is both archive and laboratory, a frozen witness to planetary history. Human exploration has also highlighted Antarctica's significance. Scientific stations study ice cores, winds, glaciers, and hidden lakes. Autonomous vehicles and satellite surveys map mountains and subglacial valleys. Each expedition reveals more about the continent's influence. Antarctica is a frontier of discovery, where patience, technology, and curiosity converge. The continent's ecosystems, though extreme, demonstrate the resilience of life. Microbial mats in subglacial lakes, plankton beneath sea ice, penguins and seals near the margins, all adapt to harsh conditions. Life persists against odds. Antarctica provides a model for understanding survival in extreme environments, both on Earth and beyond. Antarctica also holds lessons for understanding climate change. Past ice core records show natural variability, sudden warming events, and slow transitions. Comparing these to present-day changes allows scientists to distinguish natural patterns from anthropogenic effects. The continent is a guide, revealing both the resilience and vulnerability of Earth's systems. And so Antarctica's role in Earth's history is multifaceted. It is a geologic archive, a climate recorder, a laboratory for life in extremes, a regulator of global systems, and a reminder of the interconnectedness of Earth's components. Ice, wind, hidden lakes, mountains, and subglacial rivers all contribute to the story. Antarctica is not merely a frozen desert. It is central to understanding our planet, past, present, and future. The frozen continent continues to inspire exploration, study, and all its ice preserves the past. Its hidden waters harbor life. Its winds shape the surface, and its mountains and valleys influence ice dynamics. Antarctica is a living archive, an essential chapter in the story of Earth. Its lessons are vital for understanding climate, geology, ecosystems, and the delicate balance of life on our planet. And so concludes the story of Antarctica, a continent frozen in time, yet dynamic, alive and central to the history of Earth itself. The secrets it holds, beneath kilometers of ice, in hidden valleys, lakes, and rivers, in winds that shape the surface, are waiting to be understood. Antarctica's story is not just its own, it is the story of the planet.